So yeah, this talk's going to be in English, but I speak Spanish like more or less. So feel free to ask questions in Spanish afterwards. Um, so thank you all for coming. Thanks for having me here, and also thanks for staying till the very last session. So my name's Alex Morgan. I live in Barcelona, and I'm a senior engineer at Datamaran, mostly Python and Postgres stuff. And I got into tokenization to learn more about AI, because generally I saw it as roughly at the beginning of sort of like the major steps of like AI workflows. And also I think it's kind of an interesting place to start because it has, I would say, like the most parallels to linguistics, like regular linguistics, which is just personally another interest of mine. So just real quick about Datamaran. Datamaran is an ESG company that helps other companies understand their, like do risk analysis for environmental, social, and governance types of risk, which are usually overlooked. And our tech hub is in Valencia, and we actually currently have 3 positions open: a senior DevOps engineer, senior front-end engineer, and sustainability research intern. So if any of those are of interest to you, let me know afterwards. But actually, this talk is about a personal project of mine, which is like actually quite different from my regular work. And so I looked into this, these tokenization resources by Andre Karpathy, who is one of the like original founding members of OpenAI, and is relatively famous in like the AI spheres. So his overall series, the Neural Network Zero to Hero lecture series, is really great, and I think the tokenization lecture is particularly good as like a starting point. And he also has this accompanying GitHub repo called MinBPE, which is like pedagogically focused implementation of the byte pair encoding algorithm. And it's sort of like optimized to be easy to understand and learn the algorithm with. So one nice thing about tokenization is it doesn't require a lot of background. These are the main things you need to know, and it's really a pretty short list. So Unicode represents strings as a sequence of code points, numbers from 0 to a little over 1 million. And with that, you can, like represent characters from all different language alphabets, and also like some math symbols and lots of other symbols. But then in, I think, 1992, two people came up with the UTF-8 spec, and it basically uses an 8-bit format, or like 1 byte. So it's like there are 256 values from 0 to 255, because that's like 2 to the 8th power. And so they use those to represent the most common characters. And then also they still want to be able to represent all of the Unicode characters. So sometimes you have to use more than 1 UTF-8 byte. So basically, you can represent all of the Unicode characters with UTF-8, but you're going to use between 1 and 4 bytes, depending on what it is. Maybe like an emoji would take 4 bytes or something. And that is nice because it works for all languages, but it's sort of like optimized for more common letters. And then there's the byte pair encoding algorithm. So 2 years later, in 1994, Philip Gage came up with this byte pair encoding algorithm, which really simply is just saying, like, okay, if you have two tokens from UTF-8 that happen one after another, if those 2, like, let's call them letters, like happen after each other a lot, then you can merge them into an extra token, and now you have a 257th character in your vocabulary, and you've condensed your data set a little bit. Yeah? So that's the byte pair encoding algorithm. It's from the 90s, and it's actually originally made for compression, but then it got used a lot and now it's sort of like the de facto standard for AI workflows and tokenization. So now we're going to use a Taylor Swift Wikipedia article as our data set, because that's what the MinBPE repo that I worked with uses. And so here's just a sample sentence, and we're going to go through the steps of the algorithm with this text. So you start with your text from the data set. That sounds like kind of a non-step, but it's actually a really important and actually very difficult step to curate a data set. I'm not really going to go into details over that, but it's a super important step. Then you normally, especially for AI workflows, you would normally split it on something. So here I've split on spaces and punctuation, mostly. And so you notice that some of these are left adjusted and some of them are not, and it's because some of them have a space in front of them. But like IN at the beginning doesn't, because it was at the beginning of the paragraph, yeah? And so then you encode those into tokens in the UTF-8 standard. So all of the numbers are going to be between 0 and 255 inclusive. And then you're going to count the consecutive pairs of each of these tokens in your vocabulary. And so if you do that, then in that Wikipedia article, E followed by R is the most common pair of tokens. Yeah? And you can think about that in tokens, and that would be 101 and 114. But it's maybe a little easier to look at the letters. And so E followed by R is obviously pretty common for an English data source, right? So anyway, so that's the pair that you're going to want to merge. And that's going to become your new token. And so we stopped at 255, and so the next one is going to be 256. And so now you have to go back into your data set and say, like, OK, I'm going to find all of the E's followed by R's. And so that's 101 followed by 114. And I'm going to replace those with one new token, which is 256. And now I've compressed the text a little bit. In this case, it's like 2,400 characters compressed, because that's how many times that pair occurred. And then you have to repeat steps 3 through 6 until you get to the desired vocabulary size, or until you've compressed it as much as you want it to. And just intuitively, that's like a lot of work to do just to merge two tokens. And so what I'm eventually going to get to here is how you can batch those merges in a safe way. And now, so at this point, I had watched the YouTube lecture, and I had also looked at the repo, but I had to do something sort of active to actually learn something. And so I decided that I was going to try to optimize a bit the MinBPE repo, because it's kind of slow. So now I'm going to show some Python optimizations. But before I do that, just this is like very different type of code than you would normally write, maybe for like enterprise, standard logic and stuff. And so this is a very special problem that's very like data intensive. So there's literature recommendation for using about 150 gigabytes of text to create an English-based tokenizer. And so if you think about that, that's like about, I don't know, 25 billion words. And if you have to do something that processes each, pair of UTF-8 bytes in that huge text, maybe 200,000 times, because that's the general size of tokenization vocabularies that people use today, that's like a lot of work. So you really have to do everything you can to optimize it. So this is the main loop. Oh, it's a little off the, well, whatever. But this is the main loop of the whole process. And just starting with like a really simple optimization, this is almost even just for readability. I think it's better, instead of like doing a bunch of math to get to the index values that you want, it's better to directly iterate over the values that you want, instead of like subtracting 256 and then adding 256 back. So there are little things like that where you can avoid doing a bunch of math. And And then also, this is like a Python thing where function calls are very expensive. And so anytime you have to call a function, there's like a lot of overhead if you compare that to other languages. That's actually improving with each minor version of Python, but it's still a relatively high cost. So does the laser work? Yeah. Calling list here, it's a little bit faster to do the iterable unpacking into a list. So little things like that are pretty easy to find. But then you want to really get into something a little more interesting. This is the basic function that calls, that counts the occurrences of each consecutive pair of tokens. And so really this is pretty straightforward. Basically, you see what the current value is of that pair, and then you add 1 to it, and then you go back and assign it to the new value. The issue with that is that you're basically reading from that dictionary twice, and even worse, you're using a function to do that, so the get function. So if you instead use the default dict instead of a regular dictionary, then you could do that in just one call to the dictionary, and it wouldn't be a function call. So little things like that are like pretty easy to find. And then this is a much bigger thing. So this is kind of like spreading out the logic of this function, because basically this function takes it at the chunk level, which is kind of like the word level, and it's only processing one word at a time, and then you have to call the function again. But if you have 25 billion words, you don't want to call it for every word every single time you go through this loop. So if you would just put this for loop in here and have 2 for loops inside, then you could go call the function once. Yeah. And it's really not a big difference, but it reduces a ton of function calls. And then there's sort of the other half. So we saw the getStats thing that counts the pairs. And then there's the other half, which is you have to actually merge the pair that you found that's the most common. And so here we have still a lot of function calls that are not necessary. Like you don't want to have to call a function for something that doesn't change at the top of your loop. And it's actually getting called, the len function is getting called twice, when you could have just done it once outside the loop before you go in. And these append calls are used because instead of overwriting the current data, we're writing to a new list and then returning that, which is pretty standard. You usually don't want to modify the arguments that are passed to a function, but if you're in like a performance critical situation, then yes, you really need to. So the solution would be to rewrite this, overwriting it in place. And you get rid of a bunch more function calls that way. And yeah, these are maybe my favorite ones, actually. So just generally, if you think about it, the whole process is, you're going to call getStats and count the pairs and get the most common one, and then you're going to merge it. And so you're going to go getStats, merge a bunch of times. Yeah. And if you think about it, you can combine a merge call with the following getStats, because once you merge, then you already have the new state of that chunk ready to be counted again. And it doesn't really reduce any of the work, but since you already have that in memory, you've already sort of got it right there, then you can just do that other step on it, and you save a little bit of like looking for variables and things. The only thing is that means that you're kind of combining the end of the loop with the beginning of the next iteration of the loop, which is maybe like a little bit of cognitive dissonance. And that means that you have to call getStats once before you get in the loop, and then you have to also call merge one time at the end. But the interesting thing about messing around with things like that is that you start to question those ideas, and you realize that actually you don't have to call merge at the very end, because when you're doing your final merge, when you're in the final iteration, all you have to do is figure out what the next most common thing is that you want to merge, and you don't actually have to merge it because you're just trying to build up the vocabulary, and so you don't need to do the last merge. So anyway, it's little things like that that are sort of interesting finds that you can get when you're sort of digging into this. And So I would characterize all those things as kind of pretty Python specific, and maybe not super interesting, to be honest, but is very helpful to like sort of dig into how the byte pair encoding algorithm works and how you could improve it. And so I generally recommend like optimization as a way to sort of actively work with something. But now I want to talk about how we can really do a lot better. And so we just need to keep in mind a few like core characteristics of the algorithm. So basically, the number of total possible merges is always decreasing, because as you merge, then there are fewer pairs that are left, because you've condensed your thing a little bit. By contrast, the number of possible token pairs constantly increases. So that means like as you're adding more vocabulary, more to your token vocabulary, that number is like basically squared, is the number of pairs that you could possibly have, that you could possibly find in your data set. And that's always increasing, and actually increasing exponentially. And because of 1 and 2 together, that means that any given pair, as you go on, its number of occurrences can only either stay the same or decrease. Yeah? And also, just this observation that we already made, that we're doing way too much work for a single merge. So let's see if we can merge more than one thing at a time. So we already looked at E and R. That was our most common thing. And so the simplest thing would be to say, like, okay, we know that these other ones, they're either going to stay the same or decrease in their occurrences once we merge E and R. And so why don't we just look at the next one? Because we know that the second most common is going to be the most common once we merge the most common. And so the letters, or the numbers 2 and 0, have nothing in common with E and R. So there's no way that the number of occurrences is going to change once we merge E and R. So that means that it's safe to merge the second most common thing. Yeah. So basically, when we first get to E and R, we just create a set of the seen characters. And as long as the next thing doesn't reuse any of the characters that we've already seen, then we can merge that thing. And so here, when we get to E and D, we've already seen E before. So now we have to actually merge and do another iteration. So that's pretty good. That's like, twice as good, basically, or could be even better. But then it gets you thinking like, oh, well, actually, all the E's that are followed by R's are necessarily not E's that are followed by D's, because it's sort of like tautological, but that's how it works. So really what you need to be careful about is just that you can't have the same character appear in the opposite position. So if it appeared first, then it can't appear second. Or if it appeared second, then it can't appear first. So here, for example, HE is a clash, because you could conceivably have a bunch of things that are HE and then followed by R, and then maybe we would have merged the E and the R, and then it wouldn't be HE anymore. So this number is probably going to decrease once you merge E and R. Yeah, like it's pretty obvious, like in the word here or where or whatever. In English, it's going to happen quite a lot. So this step has let us get quite a lot farther. And with this, actually, I got to I think 10 times as fast as the MinBP repo. And so I wrote a Jupyter notebook, and I shared it online. And actually, Andre Karpathy replied, which was kind of cool, because it was like sort of like a jolt of energy into this project, and an encouraging thing. So then I decided to go further and create a GitHub repo for this. And so now it's called Batch PPE. And then I realized that you can actually just keep going. So when you get to a collision, you can say like, okay, when you get to a pair with a token that repeats in the opposite position, then you obviously can't merge that token, but you can add its tokens to the seen sets, and then just keep going and keep searching. And as long as you have added it to the scene sets, then you won't be merging anything else that would conflict with it or that would get its frequency changed by merging this thing. And so this is a way to actually really open the floodgates of being able to merge a lot of things. And so those were all like whether or not we can make a given merge. But then we also don't want to consider too many things. So you have to have a few things in control. So the two main ones are this one. So you don't want to, there's a really simple idea that you don't want to get too close to the edge, too close to the end. Like imagine you're building a vocabulary of 100,000 tokens, then obviously you can't consider the 200,000th most common pair because it's like definitely not going to be part of the vocabulary. It's just the wire is a little, yeah. So basically the repo I made only considers up to half the way to the end. And then also you don't want to go too far past your current vocabulary size. So basically it takes the current vocabulary size as the limit. And so when you put those two things together, this brown line is the number of things considered, the number of pairs that you can consider, and just keep in mind that there are two y-axes. And so it goes up exponentially as you start, but then about 1/3 of the way through the process, this other limit kicks in, and it decreases linearly to the end. And then here you can see this is a run with 50,000, a vocabulary of size 50,000, and you can see how many merges you can make at a time. And here I did a few different runs. This is 50,000, 100,000, and then 200,000. And basically the average batch size is the multiplier of like how much faster it goes. So here for 200,000, roughly 200,000 size vocabulary, you're doing an average of 352 merges per loop, per iteration. And so it goes that much faster. Yeah? So this is really like a huge improvement to the process. Right? And so then, yeah, like I said, I sort of changed gears a little bit, and I turned this into a repository. I also added some other features of like special handling of stop words and optional frequency cutoff. So like if maybe some like MongoDB IDs get into your data set, that's like basically useless for your tokenizer. And so you can say like if a word a word doesn't appear more than so many times, then just ignore it altogether. And some other features and things. So then I also I wrote an archive paper about this, but basically I just get a bunch of spam emails because I put my email online, right? So a more general thing I'm trying to share here is the different ways I've tried to share this project. Yeah? And so now I'm trying to share it as a presentation, and so here we are. I do have some plans for version 2 of the repo. One is that focusing on making the best use possible of Python 3.14's parallelization and multiple threads and everything. And also better support for super BPE, which I can't get into too much here, but basically that's another approach to doing like a second wave of tokenizing that that removes this step of splitting. And that has a lot of benefits, but it also has a drawback of you can't represent the whole data set as a dictionary. And so you have to use the uncompressed text. And there are maybe a few other things I want to do. But really what I'd like to share is that my new main goal is actually going from sharing a repo to trying to use this in a way that's like sort of provable that it's beneficial. Yeah, and so I was thinking of maybe trying to do some NanoGPT speed runs. And if you're not familiar with this, it's started by someone named Keller Jordan, who tried to sort of have an online competition of training the smallest version of ChatGPT-2 to like sort of the first signal of usability which is like 3.28 validation loss. And trying to do that as quickly as possible. And so they got it down from 45 minutes down to 3 minutes. And then this guy, Alex Champondard, just took the best results and then used a different tokenization approach. And it basically got like 10% better just by changing the tokenization approach. So, and actually somebody even beat this record a couple days ago, but I haven't updated this yet. And then also this week, Andre Karpathy released a new thing which is similar to NanoGPT, but it's like just the chatbot version of it. And it's a bit more expensive to train, and so it would be very useful if it could be trained faster with a tokenizer that's more appropriate to that use case. So yeah, I think a more general thing beyond tokenization is just these like changing goals in open source. And I think it's important, especially if you're working on a personal project, to sort of recognize these inflection points. And these two are in blue because they're kind of like what I'm thinking about now. Yeah. So those are the main points. I'd really like to hear any questions you have. Huh? Yes.
Thank you. It was so interesting. I'm actually not so knowledgeable about tokenization or Python, but I would like to ask you a doubt that I had about the one phase of the tokenization model that you proposed, which was when you found, for example, the E that was like in the other position. So those tokens you wouldn't consider. You would like repeat the same process as you did with in the first phase, right?
Yeah, basically you would make the earlier merges, and then you have to just make those merges and then recount all the pairs of tokens in the data set. And you're definitely still going to get the collision was HE. You're definitely still going to get those, but you're probably going to get less of them.
Okay. Will you share the presentation in the...
Sure. That slide? Yeah, maybe this is a good page for it. Yeah. So it was that ER was the first one we merged, and when we got to HE, the E is used twice. Yeah. So HE is still going to be in the data set, but the number of occurrences is going to be lower. So you can just handle that in the next iteration.
Okay.
You still have to do iterations, but a lot fewer. So we saw in this table of counts, it's like you end up doing a few hundred batches. I mean, it depends on your target vocabulary size and your data set and lots of things, but you're basically doing a few hundred batches instead of 200,000 or whatever. Yeah?
Okay, thank you.
Thank you for the presentation. I thought it's really interesting how you approach the problem, and I have two questions. The first of them is maybe super naive and doesn't have anything to do and does have no sense, but is there a way this algorithm works if you're, instead of considering pairs of letters, you consider, for example, 3 at a time, or you know what I'm talking about? So instead of merging 2 at a time, you go 3 at a time. I don't know if that's something that makes sense or has been explored. Maybe it doesn't make any sense.
Yeah, it becomes a bigger search problem because then you still have to search, like if you're doing 3 at a time even, then you have to search all of the other 3 at a times that you've considered for any of like subsets of 2 at a time that are collisions.
Yeah, and also another question is, have you considered maybe using any data structures or not like looking at the document and finding the pairs or finding that kind of dictionary? Is there maybe, as you're only using like the pairs and the numbers and then merging them, maybe a data structure that you can use to improve the process or anything like that?
Yeah, I mean, I thought that it would work better to do it in NumPy because Python object, like everything is an object, and so there's a lot of overhead to having even just an integer or whatever. But so far, it hasn't really worked out to be better. I'm sure it could be, but what I'm really interested in about this like batching process is that it's totally agnostic to Python. And so I think ultimately, if you're going to create a tokenizer for like production or something, it's probably not going to be in Python, be in like C++ or Rust or something. And none of the other optimizations I found are like relevant to those other languages, but these ones totally are, and they're actually super effective. Yeah. So yes, it could probably be a lot better than it is, but it's already, I think, a big, like, kind of a step change improvement. So I'd be more interested in trying to maybe make PRs to other tokenization repos that are in other languages, rather than like making this a bit better. Yeah.
Thank you very much.
Yeah. Oh, and also I made, I took the FineWeb 10 billion token dataset, which is like 50, 60 gigabytes or something. And I saved it as a dictionary and put it on Hugging Face. And so you can just download that representation, which is like 300 megabytes. So it's already a big condensation. Yes?
Okay. Thank you for your presentation. It was very interesting. I just have one question. What version of Python are you using, and why you want to switch to 3.14?
Well, so you can use whatever version of Python. I guess I use the walrus operator at some point, so it's like at least 3.8. But basically, like since maybe 3.10, I'd say the performance of Python's been improving quite a lot with each minor version. So you can, like, it'll basically just run faster if you use a later version, but there's not otherwise like a big difference.
I'm asking because while I'm using 3.30 last versions, it's work bad with AI, and some libraries doesn't work here. So I was asking if you using only for tokenization version, like newer versions, and for working with AI, you use like old version like 3.11, 3.10.
Yeah, I think that there were some issues with Python 3.13, which is where they first introduced the free threading mode, but you had to compile it as a separate thing. And there were some issues with some like pretty important repos, like I think NumPy and Pandas and stuff. But this is all just like straight Python. So really, you can use any version. But 3.14 is the easiest to get some improvements from parallelization.
Okay, thank you.
Maybe 3.14 was about like 25% faster than 3.12, which is what I was using before. So it's like pretty nice for kind of not really having to do anything.
Okay, anyone more? No. Thank you so much.
Thank you all. Yep.